Hello, namaste, konnichiwa, welcome to Sensei. In this lesson, I'll be talking about control charts, a key concept that's crucial not just for the PMP exam, but also for ensuring the quality and stability of our projects. Over the next few minutes, we'll explore what control charts are, why they are important, and how they're applied in real world scenarios. So, let's get started with the basics. Imagine that you run a bottling plant for Red Splash, an incredibly popular beverage. You install this machine to fill the bottles. 500 ml should go into each bottle. One of the engineers fine tunes the machine, runs some tests, looks into the results, and comes up with these two critical numbers. 500 ml, the volume of Red Splash that the machine is expected to fill in each bottle. 2 ml, the standard deviation or the variation around the expected volume of 500 ml. The quality manager now looks into these two numbers and quickly comes up with this, a control chart. He intends to use this chart to monitor and control the process of filling the bottles. So we have all this information in front of us. What does it mean and how can we use it? Let me explain. First, the engineer. She fine-tuned the machine and used it to fill a bunch of bottles. For each bottle, she noted down the volume of the liquid that was filled. These data points are our samples. She then plotted the probability distribution for these samples with the volume per bottle on the x-axis and probability density on the y-axis. The plot would have looked something like this. This plot, in common language, is called the bell curve, but engineers refer to it as the normal curve or the Gaussian plot. We will not go into the details of this plot, but still, let me point out a couple of key points. This peak is where the probability density is the highest. The volume at this point is 500 ml per bottle. This means that the likelihood of having 500 ml is the highest. Remember, we are talking about probability here. No machine can ensure that all bottles will have exactly 500 ml. This is impossible. But this plot tells us that if we fill a bottle using this machine, we are most likely to have 500 ml. 500 ml is the mean or the expected volume. This is the first number from the engineer. She also presented this second number, 2 ml, as the standard deviation. Standard deviation, or sigma, is a measure of variability. A sigma of 2 ml gives us a range of plus minus 2 ml around 500 ml. That is from 498 to 502 ml. The likelihood of ending up within this range is roughly 68.2%. In simple terms, if we fill 100 bottles, around 68 of them are likely to have a volume that falls within this range of 498 to 502 ml. Now that we have these two numbers, how did the quality manager come up with this chart? On the x-axis, we have the bottle numbers. Bottle number 1, 2, 3, and so on. The x-axis is actually representing time. The bottles are filled in order of time. The machine starts with the first bottle, then the second, and continues. The bottle number on the x-axis is mapped or is proportional to the time. On the y-axis, we have the volume per bottle. This horizontal line at 500 ml is the mean, the expected volume provided by the engineer. Upper control limit. UCL is set at 506 ml and the lower control limit LCL is at 494 ml. But where did these numbers come from? Notice that we are 6 above the mean for UCL and 6 below the mean for LCL. But why 6? The standard deviation or sigma is 2 ml. 3 times 2 gives us 6. 3 times sigma is used to define the UCL and LCL. Let me explain further using this probability distribution plot. We already know that the plus minus 1 sigma around the mean covers 68.2 of the possible outcomes. If we extend this to 2 sigma on both sides of the beam, the likelihood of falling in this range increases to 95.4%. But if we go to 3 sigma on both sides, the likelihood jumps up to 99.7%. It is common to consider 3 sigma for calculating the UCL and LCL. The idea is simple. If the process performs as expected, almost all the outcomes, 99.7% approximately, are expected to lie within these two limits, UCL and LCL. Anything outside these limits is an abnormality and requires a careful assessment. Now that we understand the background, let's go deeper into this chart by the quality manager. This chart is the control chart. We have the upper control limit, the UCL, and lower control limit, the LCL, and the mean. The mean is also known as the central line. Then we have the data points. These are the samples taken from the process over time. Let me explain. The first bottle is filled. The volume is 497.8 ml. So, on the control chart, for the first bottle, we have 497.8 ml. This is our first data point. Another bottle. The volume is 498.9 ml. So, for bottle number 2, we have 498.9 ml. This is our second data point. The quality manager continues and plots all these data points. As we discussed earlier, we expect all these data points to be within the bounds of upper control limit and lower control limit. The boundaries add 3 sigma standard deviation. There is another pair of horizontal lines that are often added to the control chart. Upper specification limit, USL, and lower specification limit, LSL. These are together called the specification limits. Specification limits are set by the customer requirements or the industry standards. Upper specification limit is the maximum and the lower specification limit is the minimum within which the data points must fall to be considered acceptable or within spec. For example, if a customer specifies that the bottle should contain between 492 ml and 508 ml of liquid, these values are the specification limits. 492 ml is the lower specification limit and 508 ml is the upper specification limit. Anything outside these limits is a defect. Let me highlight an important point. The customer specifications require all data points to stay within the specification limits. But the quality manager focuses on keeping all data points within the upper and lower control limits. For now, let's set aside the USL and LCL and view the control chart from the quality perspective. To make the chart generic, I have replaced the bottle number on the x-axis with sample number. On the y-axis, I replaced volume per bottle with sample value. I will also get rid of the data points in the second chart. There are two important terms that I would like to introduce at this stage. The control chart on the left represents an in-control process. In simple words, a process that is working as expected is a in-control process. The opposite will be an out-of-control process, a process that misbehaves and whose output is not as expected. I will use the control plot on the right to explain further. So, how do we know that a process is in control? These are the conditions. All of these should be satisfied for a process to be considered in control. We will go through these conditions one by one. Condition number 1. All data points are within the upper control limit and the lower control limit. Clearly, all data points in the left chart are between UCL and LCL. This is good. On the right, we have these data points. Here, we have this point that goes beyond the UCL. This is bad. We have a process that is out of control, and the quality manager needs to analyze further to identify the root cause and fix the process. We are done with the first point. Condition number 2. Data points are randomly and evenly distributed around the mean. For the in-control process on the left, the data points are randomly distributed. There is no visible regular pattern within these data points. This is random, and the spread around the mean, above and below the mean, is more or less the same. Now look at these data points. The points are random, with no definite pattern, but the spread across the mean is not uniform. We have more points above the mean than below the mean. The process is not compliant with condition number 2. This is an out-of-control process. Let me give another example for condition 2. Over here, these data points seem to be following a linear pattern. These are not randomly distributed. This indicates that the process is out of control, and the quality manager needs to take immediate action to identify and investigate the root cause. We are done with condition 2. Condition number 3. No run of consecutive points all above or below the center line. In the control chart on the left, the data points are randomly distributed on both sides of the mean. Now look at the control chart on the right. Over here, we have 7 consecutive points. 7 points, one after the other, all below the mean. This goes against the rule of 7. If we see 7 or more consecutive data points on one side of the mean, the process is considered out of control. Now, why 7? Why not 8? This is simply a rule of thumb that is widely accepted by quality and project managers. Moving ahead to condition number 4. Process variability is consistent and stable over time. This is true for the control chart on the left. The variation or the spread of the data points across the mean is consistent. But for the control chart on the right, the change in the spread of data points is visible, narrow initially and broader later. This is a sign of potential issues with the process. The last condition. No points show significant deviations from the general pattern. No outliers. Outliers are data points that are significantly different from other observations or data points. All is good with the control chart on the left. But over here, these two data points are quite different from others. These are the outliers. Outliers are not good, and we have a problem here. The process needs to be analyzed to identify the root cause for these outliers. I have summarized these conditions in this table. On the left are the conditions for in-control process, and on the right are the equivalent conditions for the out-of-control process. Remember, all the conditions on the left have to be satisfied for a process to be considered in control. A single deviation will lead to an out-of-control process. Moving further, here's a summary of different types of control charts. I won't go into the details. This is just a reference. Please remember that each chart has its specific use depending on what we are monitoring. Take your time to go through it at your own pace. And if you want to know more, just leave a comment below. With this, we are done with this lesson on control charts. If you found this lesson useful, please give it a thumbs up and leave a comment with your thoughts or questions. Don't forget to subscribe and hit the notification bell to stay updated with more project management lessons. Thank you so much and see you again soon.